Non-causality seems like somewhat of a strange thing in the sense that, I mean, what does it mean for the output of a system at any given time to depend on a future value of an input of the input? I mean, how is it possible that the output of the system at a particular time is affected by something that has not even occurred yet, right? So I'll try to give you a couple of examples for why we care about non-causal systems. And I mean, the short answer is this: any system that we can implement in practice is really a causal system. However, it makes sense for us to still study these non-causal systems. And I'll give you two examples to convince you as to why we should do this. Now, the easy example, the first one, is that sometimes we're not interested in systems or signals where the independent variable is time. So suppose we're interested in image processing. Let's say I have an image. An image can be thought of as a two-dimensional array of pixels, right? I have a whole bunch of pixels in an image, and here really what happens is along any row in the image you can think of it as a signal. However, when we do this, the independent variable here is not really time, but it's really space, right? When you think about it this way, it makes more sense for a system to be non-causal in this sense. In the sense, if n were to represent space, I'll give you an example for something that makes sense. Now, let's say I have an image, and an image typically represents, you know, a picture of a terrain or a picture of a face or something like this. And usually, the pixel values do not really change drastically from one pixel to the next, unless you are in an edge in an image. Right? For a large part of the image, the pixel values do not really change substantially from one pixel to the next. However, let's say that we have a noisy version of the image. So in other words, we have an image and there is some noise added to the image, but the noise values change substantially from one pixel value to the next. Okay. Now, if you want to denoise this image or try to somehow remove the effects of noise, one thing that you can do is you can average the value of the noisy image around a small window and replace the value of this pixel in the noisy image by the average value of these three pixels. You may want to do this in both dimensions, but I'm just giving you one example to try to relate to something that we have already seen before. Now, when you do this, if x of n represents the value of the pixel along the x direction in let's say the second row of the image, then mathematically all we are really doing is we are replacing the value of x of n by an average of x of n minus 1, x of n, and x of n plus 1. Right? Mathematically, this system is identical to this system 2 that we looked in the previous video, and we know that this is a non-causal system. And clearly, this is something that you can implement in practice, and this is one reason why we are interested in non-causal systems. Now, the thing with the noise varying substantially is to say that this kind of an averaging operation makes sense because x does not change too much. I mean, the original value of the image does not change too much across 3 pixels, but the noise value may substantially change. So when you average the the noisy pixel values, you can get a substantial reduction in the contribution of the noise without leaving the original image disturbed too much, or leaving the original image undisturbed. Okay. Now, I'm going to give you a second example from audio processing. All right. In the second example, let's say that you are streaming some music file over the internet. So I've drawn a picture here where the black signal here represents the actual music that you're streaming. But let's say for whatever reason that you have received a noisy version of this signal. So the red signal that I've drawn here is a slightly noisy version of the black signal. And what it is that I took the black signal, and if you added some noise to this, so the values are slightly different. The red values are slightly different from the black values, right? Now, one intuitive thing that you can do to try to clean up this noise is to kind of replace each value of the noisy signal by an average taken around a small window, right? So for example, what I can do is, let's say x of n was the noisy signal. So this is the red signal. Now, what I could do is I could average the signal. So for example, let's say I take the average of these three signals and replace this value by the average of this. You can intuitively see that this is going to kind of smooth out or reduce the noise. So particularly here, I drew an illustrative example. You can see that the noise is sometimes larger than the signal, sometimes smaller. So if I were to take the average, I would kind of average the noise out a little bit, right? So a sensible thing to do here again is to replace the value of the audio signal at time n by an average of the noisy signals at time n minus 1, n, and n plus 1. Right? Now, if I do this, clearly this represents a non-causal system. Okay, so this is another example for why we are interested in non-causal systems like this. Now, let's think a little bit about how do we actually implement this system. Well, notice that this system can be implemented if you allow me to buffer this signal. So what I'm saying is, now in order to produce y of n at time n, I will need to wait until I receive x of n plus 1, right? But if you think about streaming over the internet, then all this really means is that you are streaming the signal, so the signal is arriving at your receiver, and if you buffer one sample of the signal, actually if you keep x of n plus 1, x of n minus 1, and x of n in a buffer, so you could think of a buffer and the signal x of n coming into this buffer, and you keep x of n minus 1, x of n, and x of n plus 1 in, well, maybe I should draw it like this, in the order in which these samples come in, right? Then I can take an average of these two and I can form the signal y of n. So in this sense this is practically implementable. It's practically implementable even though this system appears to be non-causal. So what we have hidden here is truly the fact that with some buffering, really speaking, the system is causal, right? Once I have buffered the signal, then I've kind of delayed the signal x of n. So it's like first taking x of n and then delaying x of n by 1, forming a new signal called x tilde of n, which is actually x of n minus 1. I'm sorry, I think this is not x of n minus 1, this is x of n plus 1. So I form a new signal x tilde of n, which is x of n plus 1, and then I'm really operating on x tilde of n. Now you can see that y of n is actually 1/3 of x tilde of n minus 2 plus x tilde of n minus 1 plus x tilde of n. And this is really a causal system, and this is what we actually implemented. So the point is, non-causal systems can be implemented with a delay, or in other words, they can be converted to causal systems with a delay, and then we can implement them. but it's just mathematically nicer to think of this system, or it's easier to think of this system than this, and this is why we are interested in non-causal systems.